Quadratic equations are fundamental in algebra, and understanding how to visualize them helps us solve them. This is the standard form of a quadratic equation where a, b, and c are constants and a is not equal to 0. This algebraic expression represents a parabola when graphed. Let's visualize a specific example. Y equals x squared minus 2x minus 3. This equation creates a parabola that opens upward because the coefficient of x squared is positive. The x-intercepts of this parabola are the points where the curve crosses the x-axis, meaning where y equals 0. These intercepts represent the solutions or roots of the equation x squared minus 2x minus 3 equals 0. Since we can identify the roots as -1 and +3, we can rewrite this quadratic equation in factored form. This is one method of solving quadratics when the roots are rational numbers. Each factor corresponds directly to a root. When x equals -1, the first factor becomes 0, and when x equals +3, the second factor becomes 0. This makes the entire expression equal to 0, confirming our solutions. However, factoring only works easily for certain quadratics. Many equations don't have simple factors or nice rational roots, which is why we need a more general approach like the quadratic formula. Consider this new equation, y equals x squared plus x plus 1. Unlike our previous example, this quadratic can't be easily factored because it doesn't have rational roots. Looking at its graph, we can see that this parabola never crosses the x-axis. This means the equation x squared plus x plus 1 equals 0 has no real number solutions. The roots are complex numbers, which we can't visualize on this coordinate plane. The vertex of this parabola is at the point -0.5, 0.75. Since the y-coordinate of the vertex is positive and the parabola opens upward, the curve will always stay above the x-axis, confirming there are no real roots. This is where the quadratic formula becomes essential. It gives us a direct method to find all possible roots of any quadratic equation, whether they're real or complex, without having to rely on factoring. The graphical perspective helps us understand why we need the quadratic formula. When a quadratic is easily factored, we can find roots through factoring. But for quadratics with irrational or complex roots, we need a more powerful and general solution method. We start with the standard form of a quadratic equation, ax squared plus bx plus c equals 0. This is the form we need to identify the key components of our equation. In this standard form, a represents the coefficient of x